So, we wend our way further on determinants. So, last time I ended with the definition of a 3 by 3. That if you had 3 vectors in R3, it looks like a very strange definition. And as I said, you'll understand where it comes from much better next semester. But what we said was, think of the first vector as being singled out and use the coefficients, the coordinates of the first vector times 2 by 2 determinants of what's left over when you remove that entry and its row. So x1 goes with this determinant. And you're going to see in a few minutes that this leads to very pretty geometry going on with this. So x2 with a minus sign, which I warned you about last time. Most times if you have a computational error computing the determinants because you forgot that minus sign, or you screwed up minus times minus somewhere else. Okay, so you have this definition. And I did point out if you expand this out, you'll get 6 terms, right? Because each of these is 2 terms. So you'll end up with 6 terms. And what I pointed out is that there is a shortcut, which you can do by copying down the first 2 columns yet again on this side, and then take products going down to the right, like this, and then up to the left, like this. Well, I don't know what's meant by to the left. That's going up to the right, but those give you negatives. So this generalizes the idea of a 2 by 2 where you do plus there and minus there. The warning for those of you who are tempted is it will not work in higher dimensions. So when we get to higher dimensions next semester, don't try to do this, it won't work. Now, those of you who get really good at this, should be able to do the determinant faster and faster. So, for practice, how are you going to compute this?
28 5 and 9 minus
28. So you're doing this, or you could do 2 times this determinant, right? You could do 14 plus 3 minus 1 times this determinant, negative 2 minus 5, plus 3 times 3 minus 35, and then you have horrendous arithmetic to do. 96, what is that? 41 minus 96. Now those of you who get good at this can do the following. 2 times 7 times 2, plus negative 1 times negative 3 times 3, plus 5 times 1 times 1, minus 3 times 7 times 5, minus 1 times negative 1 times 2, minus 2 times 1 times negative 3.
Yeah, sure. Yeah.
You say it like it's hard.
It's not hard. It's just hard to say that. So this pattern, doing this, you can actually do hopscotching through the matrix if you've practiced. So you see that you're doing this, and then going back like that.
Yeah.
That's exactly what this is. Okay, so if you want to win a speed round in some ridiculous competition, that's important. Otherwise, it's not important at all.
Isn't your test like a speed competition though?
What? You get an A if you turn it in first.
No, I mean you have to be able to finish the test.
So I suggested to you guys that the 3 by 3 determinant should have the same ilk of properties that the 2 by 2 did. So for what was the first property we observed when we had 2 by 2s, we said that if you took, I'll stick with x, y, and z, I guess. If you switched x, and when we had 2 of them, if we switched it, we got a minus sign. Well, same thing's true now. If you switch any 2, so you can switch x with z, and you can switch y and z, you get a minus sign. What happens if you do the following? Why should it equal the first one?
Because you switch signs twice.
You switch signs twice. So you could think about getting yzx by switching x and y back and putting x here. And that would give you one minus sign. And then you could switch the y and the z, and that would give you yet another minus sign, so it would make it plus the original, which is what Alex said. So given any particular switching around that you do, you can figure out how many minuses it corresponds to. There's a fancy word for that you'll learn next semester. What was property 2? Anybody remember? Scalar. So if you scale any one of the vectors, what do you think it should do to this formula?
Pops out.
Just scales it.
The scalar should pull out. And in fact, it now follows that if I do the scaling in any of the vectors, it's true, without having to make a separate statement. Because by this property, I could think about switching that vector to the first slot, scaling, and then switching back. Did you understand what I meant by that? Or you could just check from the formulas. All right, the more interesting one, oh, and I forgot one in the 2 by 2 case, actually. I just remembered it for now. The next one was the more interesting one, that if you put a sum of 2 vectors in one of the slots, you get the sum of the determinants. And again, I'm going to make the claim that you can do that in any of the slots. So if you put a sum in the first slot, you would get the sum. Once again, you could be lazy and say, I can switch slots using property 1 and then switch back at the end. So you only have to do it for one of them. But I'll still make one comment about this in a minute. And the last property, which I did forget for the 2 by 2, but it's still important, is what happens if I put in the standard basis vectors for my vectors? So, 0.
No. 1 plus 0 plus 0 plus 0.
So I have
1 plus 0
1,
plus
0, 0, 0, 1, 0, 0, 0, 1.
Play hopscotch.
So you can see from this way of thinking about that, you only get one term that isn't 0, and that's this one, 1, 1, 1. All the others have zeros in them. Now, this is consistent, and again, I should have commented that in the 2 by 2 case. This is consistent with our signed area / signed volume interpretation. This is saying that if you took the unit vectors and made a cube out of them, that it would have volume, signed volume 1. Now, I haven't yet told you what signed means. I will tell you that later today. Okay? So algebraically, do these all seem to make sense? Well, if I switch y and z here, then that switches all of these, and we know that makes these negative. It is not obvious to me that if I switch x and y, that I get the negative. Matthias, do you have a comment?
Well, this is kind of because because you don't necessarily have to use x1, x2, like in that formula. You could use instead of like take the third column.
But we don't know that though. I mean, so this is my definition, right? So, I mean, you're right, and we'll again discuss that in much more detail next semester. But from this definition, it's not obvious that if I switch these two and work out the algebra, it will work out. So that actually, so I'm going to just say verifying 1 for switching the first two, I'm going to say is unenlightening algebra. So does that mean you have to be careful with the algebra in bad weather? I don't know. But you can, I mean, you just write out the formula and you see it works. I don't have, from the algebraic perspective, I don't have a good solution to that one. Mm-hmm.
So we're talking about determinants of for the vectors, but this also applies to matrices transformed. So does it have anything to do with like the ratio of the magnitude of a vector before and after it's transformed? Because when a rotation is always 1 with a determinant, and same with the unit vectors. So and those have changed the magnitude. So
What doesn't change?
the magnitude.
Oh, you're thinking about rotation. Yeah, so we will in fact discuss that in detail next semester. What Matthew's asking about is thinking of a matrix rather than the columns of the matrix per se. What's the geometric meaning of the determinant of the matrix in terms of the linear transformation itself? And so I'll answer the question, in fact, to be continued next semester. So for 2 by 2, if you took a matrix A and you thought of it as 2 column vectors, you thought of that representing a linear transformation from the plane to the plane, what's the meaning of A1 and A2? Well, it's 2 vectors, right? But where did they come from? They came from applying that linear map and seeing where what went. Standard basis vectors. So what we do know is that this determinant of A, the determinant of this matrix, is the signed area of this parallelogram. What's the signed area of the original parallelogram? 1. So the determinant is telling you what T does to area, or to signed area. When you map vectors here to vectors there, it multiplies the area by, or the signed area by the determinant of the matrix. Same thing for volume with 3 vectors. Take box, it maps to a parallelepiped. The signed volume of that parallelepiped is the determinant. And so, and this will be crucial when we do integrals next semester, the determinant is coming in as a fudge factor that says how area or volume is distorted. So more next term on volume, on determinant as fudge factor or distortion of sign volume. Okay, so that was an aside. Good question on that. Okay. Verifying 2 is obvious. If you put a scalar in, either it pulls out of the x's or it pulls out of the y's or the z's by what we did for 2 by 2's. This linearity, what happens with a sum, we already proved that for 2 by 2's. So if I put the sum in either of these slots, it follows from what we did for 2 by 2's. On the other hand, if you put the sum in the first slot, then you immediately see that you just have the distributive law because you have x1 plus w1, where I have x1 there, and x2 plus w2, etc. So you just have a sum. So the algebra is easy to check, except for number 1. So I'm going to tell you without belaboring it, because we did talk about it for area, as was the case with signed area last class. These transformation properties, these algebraic properties, have geometric interpretations. So if you, once you've decided, well, I'll tell you what sign. The sign on sign volume goes like this. And this will make more sense in a few minutes. If I have x, y, and z, I'm going to say, think of the parallelepiped. X and y make a parallelogram. You can think of a plane that x and y determine here. Now, I'm going to have to say something that will make more sense in a few minutes. Think of a right-hand rule here. So if x is rotating counterclockwise towards y, think about taking your right hand, because if you're left-handed, it's backwards. Take your right hand, do x, curl your hands towards y, and your thumb points in a certain direction. If z is on that side of the plane that your thumb is pointing, so a good artist here could draw me a hand and a thumb pointing up. I'm not a good artist. If the z is pointing in the same direction as the thumb, then the sign volume of the parallelepiped will be positive. If the z is pointing down on the wrong side from the thumb, then the sign volume is going to be negative. So if you switch any two of the vectors, you're going to change from one to the other. If you switch x and y, that switches where your thumb points to the other side. Matthias?
Now this might be going a little bit ahead. So, okay, so basically you're saying if the angle between the cross product of x and y and z
I haven't
is-
gotten to that
okay,
word yet.
so-
That's why I wanted to say that,
Okay.
yeah. So that's where I'm headed next. So as we discussed with shearing rectangles, this property basically is equivalent to saying that if you shear a parallelepiped, that you don't change the volume. And I drew you a picture for this in the general case for parallelograms. I'm not going to try to draw pictures for the sign volume. 2 is equally obvious because you're stretching one of the sides of the box. 4 is just saying the unit cube has sign volume 1. Okay, so I'm going to say that if you wanted to work very hard playing around with three-dimensional pictures of boxes, you could actually do what we did for the plane on Wednesday and check all of these geometrically. I'm not going to do that. But, so by the way, if you have a signed volume of a parallelepiped and you want to know the actual volume, what do you do with the signed volume? Take absolute value. It's the same number as if it's positive, and you take the negative if the signed volume is negative. The actual volume is the absolute value. That's relevant for web work, of course. Okay, so I now want to use this to do the word that Matthias said. So this is for doing three-dimensional vector geometry. This is crucial. I want to take two vectors in R3 and create from them a third vector. So given u and v in R3, I want to define a third vector called the cross product. And let me warn you, this works only in R3. You can't do this in R4, you can't do it in R5. There are generalizations of this idea which you will learn next semester. But for all your friends who think they can do cross products of two vectors in R4, they're out of luck, they can't do it. That's why physics is so special in 3 dimensions and they have to worry in 4 dimensions. Okay, here's what you do. So symbolically, I'm going to write down something that you're going to look at and say, that makes no sense, but I'm going to tell you to do it anyway. You take u cross v to be the vector you get by doing a determinant, where in the first column you put e1, e2, e3. And you're already saying that makes no sense. I only know how to do determinants with numbers. And I'm telling you, I don't care. Do it anyway. Put u in the second column, and put v in the third column, and do the determinant. Well, for all of you naysayers, all I mean for you to do is write down the right-hand side there, where x1, x2, x3 are replaced by the vectors e1, e2, e3. So by definition, I mean e1 times the vector, times the scalar, that's the determinant of the bottom part of the u's and v's, u2, v2, u3, v3, minus determinant u1, v1, u3, v3, e2, plus u1, v1, u2, v2, e3. Please don't memorize this. Just think determinant and do the determinant as we were discussing. All right, so let's do a computation. I'll let you guys race me. Okay, so example. What is the cross product of 1, 3, 4 with -1, 7, -2? So either write stuff down or do it in your head, but one way or the other, I want you all to do the answer. I can give you the answer.
Are we determining who the quickest is?
Oh, I should have offered a prize.
That hurt.
But yeah, I'm not even deigning to lower myself.
14.
Well, the answer is going to be a vector whose components are.
Oh, it's 22.
Say what?
-10 to 34? I just started.
No. First one's wrong.
Negative 30.
Negative 34
2.
negative 2.
Negative
Next 31.
Two.
Negative 34, negative 2.
3, 2. Mine's low. Oh, yeah.
That's what I said. I said the opposite of that,
Yeah.
which is That, I mean, that's the same. Just going in a different direction.
Well,
Would you say that going north is the same as going south?
Now we understand why Jonathan gets lost so much.
We'll get there eventually.
How many people got this?
I only got the first one.
You only got,
negative half.
I only got negative 34.
so for the middle one, remember I'm taking this determinant. I remove the middle row, I'm doing -2 minus -4, so that's +2, but then there's this minus sign that I warned you not to forget. So while you guys are doing web work and while you're doing this stuff in life, determinants, there's so many places you can make sloppy mistakes. You can forget a minus sign, you can also forget to subtract a negative.
What if you said it was plus U3 V3 U1 V1?
Then you'd be correct. And we will get back to that next semester. Yeah, that's fine.
Yes, I got something.
Okay, so now I'm just sort of curious here, and so all of you guys who know this already, do everybody else a favor and keep quiet, and I try to get the people who don't know it to discover something. I'm just curious though, for those of us who haven't seen this before, what might happen if we took this vector u, this vector v, and this cross product, and I asked you, what do I get if I dot the original vectors with my answer? -34, dot, right? Dot product's a number. Cross product's a vector. Dot product. 1 times -34 minus 6
plus 40.
plus 40. Interesting. What happens if I dot the second vector? I did?
We jumped out together.
I liked you better when you were sick, Alan.
I still like that.
I'm just gonna go on a limb and say it's gonna be 0.
What do I get if I do this? 34
minus
14 is 20.
minus 20 is.
So mysteriously, when I compute the cross product, it comes out orthogonal to the original vectors. Can we see why that's true from the definition? So note, in general, u dot the cross product and v dot the cross product are both 0.
Why'd you say in general?
Because generally.
That usually means that there's some example that it's not.
No. So we just did an example where it worked, and this is going to hold always.
Oh, what?
So I want to give you a general reason for understanding that. So here's a little lemma for you that's actually sort of cool. If you take a vector z and dot it with u cross v, that's the same thing as doing the determinant of the matrix that has z, u, and v as the columns. So what am I doing when I do the cross product? I'm doing a vector that has these various determinants as the coefficients. What if I wanted to do z in this first column of my matrix? I would have z here, and then I would have u, and then I would have v. And so what would I get? I would, by our definition of determinant, I would have the first z times this determinant. And then I would have the second component of z times the other determinant with u1, v1, u3, v3, and then z3, u1, v1, u2, v2. How is this related to that cross product thingy
You're basically using the e's as a placeholder.
Here I've got the e's as a placeholder, and if I just dot this with z, I take the first component of z times this, plus the second component of z times this, plus the third component of z times this. Well, that's exactly that. This is exactly the dot product of z with the cross product of u and v. Well, once you can see this, then this is now obvious. Why is this now obvious? What do I want to substitute in this formula to do this? U. So U dot cross product is determinant of U, U, V. Now, I didn't say this today, but we said it on Wednesday. What happens to a determinant if you repeat the same vector?
Several.
Why?
Because it equals its negative.
Okay. So remember you guys gave me the argument the other day that it followed from this rule, very conveniently, from this formula, it follows that if you put the same vector in twice, you get 0, because if I switch the two, I'm supposed to get the negative. Well, that x and that x still look the same to me, even though I switched them. So whatever number this is, it equals its negative. So I get 0. And same thing if I switch the other two slots. So duuv is 0 and dvuv is 0 because I can switch those two and change the sign. So that proves this. Okie dokie. So what does this tell me? This tells me that if I take the cross product of two vectors, I get a vector orthogonal to their plane, orthogonal to both of them. So if I have u and I have v, the cross product is somewhere in the perp of that plane. Right? But the plane they span, and the cross product is somewhere orthogonal to the plane. But I know not yet whether it's pointing up, nor how long it is. So you know it's perpendicular to the plane, but you don't know its magnitude, and you don't know which direction it's pointing perpendicular to the plane. So I'm sort of curious to figure those out. So what is the magnitude of the cross product?
Just Pythagorean?
Isn't it the parallelogram, like the area?
I don't know, is it?
Yeah. It is.
Okay, I don't want to erase this because I want to come back to that. So, what would I get? We do have, so we're interpreting this determinant as sign volume. I think I'd like to consider a box, a parallelepiped, whose sides are u, v, and the cross product. What can we say about d of the cross product u and v? Well, first of all, this is the same as putting them in the order I just said. Why is that? Right, we're back to the thing I did that I just erased. Remember we said if you cycle these around, It doesn't change the sign. So I could switch these two and get one minus sign, and then switch u cross v and v and get this, so it would have had two switches. So it's the same sign. So this is the picture. This is the sign volume of the box, parallelepiped, with size u, v, cross product. Okay. On the other hand, what did we just prove in our lemma? What does our lemma say we get for that? I put u cross v, uv, do the determinant, it's the same as what?
U cross G dot itself.
I take the vector z that's sitting in this slot, and I dot it with u cross v. Okay.
Wow.
So what have I got? I've got I'm going to draw the picture again for convenience. I've got a box with a base made by u and v, and then u cross v we already said was orthogonal to the plane of the box, of the parallelogram. So what kind of sign volume are you going to end up with if you take a parallelogram and then a vector that's perpendicular to the parallelogram?
A scale.
How do you do the volume of such a thing?
It's the magnitude of u dot v times the area of the parallelogram.
Say again?
It's the magnitude of u, cross v, sorry, times the area of the parallelogram.
Yeah, it's the height times the area of the base. Because this vector is orthogonal, the height of this box that I would draw here, the height of that box, didn't quite do that so perfectly, the height of that box is exactly the magnitude of this vector. So the volume is the area of the base times the height, which is the length of the cross product. So what do I conclude if I juxtapose these two ways of looking at the volume?
Magnitude of U cross V is going to get.
First of all, I notice that the signed volume is positive. So it equals the volume. So first, the signed volume is positive. Secondly, I have this number equals this number.
It's got to be positive.
So area of the base, the area of the parallelogram spanned by u and v, is the magnitude of the cross product. Very cool. So determinant of two vectors in the plane tells you signed area. Taking the magnitude of two vectors cross product in R3 gives you the area of the parallelogram in R3. But now this also tells you, if you put this picture together with our lemma, you now see what I was saying earlier and couldn't quite say the way I should have. What are we saying here when I was talking about the thumb and saying z should be on the same side as your thumb? Well, if you put the cross product consistent with the right-hand rule, if you orient your hand going along x, turning your fingers towards y, then your thumb points in the direction of the cross product. And now we're saying that when z dot that cross product is positive, namely when z is on the same side of this plane as the cross product is, then you have positive sign volume. And when z is pointing opposite, you get negative. So the cross product points perpendicular to the two vectors. Its direction is given by the right-hand rule. And the magnitude is given by the area of the parallelogram. Everything you need to know. Any questions? So if I go back and I ask you, what's the area of the triangle with vertices, the origin, the vector 1, 3, 4, and the vector -1, 7, -2, what's the answer going to be? So I've got two vectors in R3, whatever in the world they look like, I have no idea, but schematically, I can draw you two vectors. They span a parallelogram. I'm asking about the triangle now, whose vertices are the origin and the tips of those vectors. How do I get the area of that triangle? So if I take the cross product of the two vectors, that gives me a vector which we happen to have computed. It's got ridiculous numbers in it. -34, 2, -10.
Positive.
No, -2 and +10. What we have just established is that if I take the magnitude of the cross product, that will be the area of the parallelogram. And so if I want the triangle,
You divide by
I take half, right? So therefore, the area of the triangle is 1/2 the magnitude of the cross product. Now, conveniently, I did not knowingly create it this way, but what did we notice? We noticed that the vector consists of even numbers. So rather than finding the length of this vector and then dividing by 2, what would I rather do? Take the 2 out to start with. In fact, in general, remember, if you want the length of a vector, you can factor a number out, pull the number out, and then do the square root of the sum of the squares. It'll make the algebra easier. So the answer is going to be 1/2 the magnitude of the vector is going to be the magnitude of 1/2 the vector, which is going to be the magnitude of -17, 1, 5. Piece of cake. Oh, -1. So I actually happen to know what 17 squared is. 289. Plus 1.
I got that one, that's 1.
Okay. We're up to 290. Plus 25.
Which also works out to be the square root of 1260 over 4, or over 2, so.
I can't do that really good. I barely made it to this. Any questions on any of this? Although, okay, so one additional thing that's useful here, although I didn't think originally when I made the Weber assignment I was going to get to what I'm about to say, so if you don't have it on Weber, it will be on there on the next assignment. This is also good for me. This computation that we did here tells me something in addition. remember one of your favorite homework problems where I asked you to show that an equation of a plane was the same as the set of points satisfying an equation a dot x equals 0 was the same as being spanned by two vectors? That was in the homework you just turned in the other day. Well, I could ask you now to consider the plane that's spanned by 1, 3, 4, and -1, 7, -2. And that plane is sitting somewhere in R3. I'm not going to draw it to scale. But I would like to write V in the form A dot x is 0 for some vector A. How do I find a vector A? The cross product, because I want a normal vector to the plane. I want a vector that's orthogonal to all the vectors in the plane. Well, if the vector is spanned by, if the plane is spanned by these two vectors, we just found a vector that's orthogonal, namely the cross product. Take A to be the cross product, or any scalar multiple of the cross product. So to make my number simpler, I'll divide by -2, and I'll put 17, 1, -5. You could take any non-zero multiple of this vector you wanted. But this is a vector that by construction is orthogonal to both these vectors. Therefore, by your homework problem, it's orthogonal to any linear combination of these vectors. So that means this plane is the set of vectors x satisfying the equation 17x1 plus x2 minus 5x3 equals 0. Everybody got it? So you now know how to go back and forth. In R3, given a span, you can now create the equation, and you already did in homework going from the equation back to the spanning vectors. You've done that too. Now what I'll talk about on Monday is what we would want to do if I wanted to take this plane and slide it parallel to itself and get a plane that was shifted over. So we will discuss that on Monday.